Hello everyone. In this video we are going to talk about the Principal Component Analysis PCA, which is one of the methods of dimensional reduction or dimensionality reduction, basically bringing down the number of features that you would consider for any machine learning purpose classification or anything else. And you can also use it for data compression. It is an unsupervised method, so you do not need to give it any output or any target value. Now, let's talk about some motivations and then how this method is done. So let's say you want to recognize handwritten numbers, right? So if you consider here this number 3, and these are pictures of number 3 written by several people, say 5, then let's say each one of these images is just 100 by 100 pixels. So just very small image, not HD, nothing like that. So 100 by 100 means 10,000 pixel values. So if you want to recognize or classify one handwritten number 3 among so many others, then the number of data values, the number of data points that you need to store, the size of the feature vector that you need to store the values of each and every one of these 100 by 100 images is 10,000. That's the size of your feature vector. And now, if you want to store 5 of these, that's 50,000 values, right? If each value is 8 bits, right? They are uint8. That's 8 times 400. That's 50,000. That's 400,000, or something close to like 400 kilo bits, right? Or 50 kilobytes is what you need to store just these 5 images. And so you see, for a more complicated task, the amount of storage goes up significantly, and the same way goes up the computation time. So what you can do, you say, well, actually, if I write this number 3 like this, how many different ways I can manipulate this number 3 in a 100 by 100 background to make it look different? When one of the simple thing you can do is to move it along the x. So 1 3 is like here, the other 3 might be like here. Or you can move it along the y direction, right? So 1 3 is like here, the other 3 could be like up here. Or you can rotate it, as you can see with some of these. So one of your 3's could be something like this, correct? So a rotation would be another kind of possibility of changing this appearance. What else? The scaling, right? You might have a small 3 versus a large 3, or the line thickness, correct? And a few other deformations are all you can do to make the shape of this 3 different from its, let's say, typed version. So ideally, the number of different ways you can distort this 3 is not even probably going to reach 10, but guess what? You have to store 10,000 values, a vector with 10,000 values to look at all these different pixel values. So definitely that size for the feature vector is an overkill, right? You are just storing too many data that are redundant, that are not playing a big role in digit recognition, that are correlated with each other, and so on. That's where PCA comes in and say, hey, I do not need all of that. Out of these 10,000, maybe I just need 5 or 10 or 6 or 20 of them that would really play an important role in classification here, and the rest of them are not playing any significant role. So that's what we're going to do with PCA. So what is it that you do? You project your data, those huge vectors, right, of features, you project them orthogonally to some space that is much lower dimension. Okay, so use orthogonal projection of all of these data points with a huge number of entries. You project them to a lower dimensional space, linear space. That space is called the principal subspace. And the dimension of that is way, as I said, less than 10,000. 5, 3, 2, 5, 6, something like that. We'll see how many. It depends on the application. It depends on how the system behaves, but definitely much, much smaller. Okay? And now, what's the goal of the PCA? Well, if let's say we say 5, right? Then which 5 vectors can we choose, right? So let's say in this case here, my datas are xn, where n goes from 1 to 5. I have 5 data points, but the size of each one of these xn's is what? Is 10,000 by 1. So the dimension d is what? 10,000. The number of data points is 5 data points. And my goal is to reduce the size of these xn's to something like you might call x tilde of n, where the size of that x tilde, which is approximation of xn, is like, for example, 6 by 1. And this 6 is the lower dimension m that we are going to talk about. So now, what is the goal of PCA? The goal of PCA is how do you do that? If you have to do a projection, what you need is what? The basis vectors for that subspace, right? This principal subspace, it has a basis. And this basis for this subspace, if you call the vectors forming that, if you call them u1, u2, and so on, correct? So let's say I have some u vectors. The size of those u vectors is the same size as xn, so they are all 10,000 by 1. So we can use those to project xn, but how many of these u's do you have? You only have m of them. So you only have u1, u2, all the way to u6. You will only have 6 unit vectors. By the way, these u's, since they form a basis, we use unit vectors for all of you. So each one of these u's is a unit vector, and since they are bases, they are all perpendicular to each other. So u1.u2, u1.u6, and so on, they're all 0. So now, how do we do projection? You know, for projection, all you need to do is to dot product these u vectors with the x's, right? Then you project each one of these x's onto this subspace. So you can say that your x tilde of n is going to be what? It's going to be a linear combination of basically these u's. So it is like alpha 1 u1, correct? Plus alpha 2 u2 plus all the way to alpha 6 u6. These alphas are just scalars, and they are weights of this linear combination. And then you can show that, for example, alpha 1 is what? It's u1 dot xn, or if you want to use transpose, you can say u1 transpose times xn tilde. Times xn, I'm sorry, not xn tilde. Okay, so if this is alpha I, you can say ui dot xn, or transpose of ui times xn. Okay, so this is projection. We know all about projection, and I'm not going to go into linear algebra, but that's what we are going to do. And there are 2 different ways to do the formulation of principal component analysis. One is we call the maximum variance formulation, and the second formulation is the minimum error formulation. I'm going to tell you both, as each one has something to teach us. Okay, so I'm going to go through both of them, but the goal is the same. You have n data points. Each one of them has a dimensionality of d. We are going to bring that d down to m. M definitely is less than d, and m is a given parameter. So the 6 that I talked about here, we selected, or it's given to us. But I'll tell you in the remaining of the video how we can decide a good value for M. This plays similar role to the K in K-means clustering. That is the main parameter. So how do we do it? What's the goal here? What's the cost function? How do we perform the formulation? The goal is this. We project the d-dimensional x's into m-dimensional x's, but we try to make sure what? The variance of this projected data is maximum. Why should we do that? Because remember, if we want to do, let's say, classification here, the goal is to make each one of these what? As long as they are all 3, you want all of them to be clustered close to each other in the lower dimension space. If they are 6s, they should be close to each other, but definitely in a different location from the 3. If they are 5s, again in a different location, and so on. Or if I want to show you a better picture, let me show you this picture, which is one of my favorites. This one here. Let's say my goal is I have here 15 faces. And what I want to do is, as I said, let's say each one of these pictures of these people is so many pixels by so many pixels, right? Let's say 100 by 200 pixels. So each one of them contains a dimensionality of 20,000, right? So what should I do? My goal is I bring down that, let's say 20,000, let's say to 3 here. I only project everything to a 3-dimensional space, let's say, such that different pictures of the same person go to one corner, different pictures of another person go to another corner, and so on and so forth. Right? So instead of 20,000 dimensionality, I brought it down to 3, yet I make sure these 3 are chosen that the data belonging to the same object all cluster in one corner of this space, the data for another object cluster somewhere else, and the variance among these clusters are maximized. Because if I don't maximize it, I can still bring it maybe down to a 3 or 4 dimensional or something space, but then these clusters are going to be so close to each other that if I want to run, let's say now K-mean clustering and say, hey, these pictures are here, those pictures are there, and I have 3 people in this whole set, or 15 people, then because these clusters are so close and the variance among them is so low, I'm not going to be able to easily do the clustering. Okay, so remember, typically use PCA before what? Before you do a classification or a clustering or something like that, right? Because you don't want to deal with these higher dimensional data, which need a ton of computation and a ton of storage. You remove the redundancies, you bring it down to the minimum required dimensions or data, then do the clustering. Yet you want to make sure the clusters are easily distinguishable from each other. That's why you try to maximize what? The variance of the projected data. That's very important. So how do we do this projection? For now, let's just assume that you only have m equal 1. In other words, you want to bring down the d dimensions only into one single dimension. You just want to choose one single data or a projection of all this into one single data, and that single data is basically showing a ton of what? A ton of variance, right? So basically, in this case, if I go back to that picture, instead of this 3-dimensional, I want to have one single axis, but all of these pictures come here, all of these guys go there, all of these guys go here. So I only have one single U1 for a moment. Let's just assume m is equal to 1. Here m is definitely what? 3. So what do I do? First, how do I do the projection? That's very clear. The projection of data point xn is going to be u1 transpose times xn, just like I told you, correct? That's the projection of that. By the way, here I use the notation x bar as the average of the original data points. And if I want to project the centroid of the original data points onto this new space, I can say, again, the projection is going to be U1 transpose times what? Times x bar. So this is the projection of centroid of the data. This is the projection of what? Each and every one of the data. So now how do we calculate the variance of the projection? So this is the projection of nth data. This is the projection of the centroid. If we subtract and raise it to power 2 and then divide it by the number of data points, this is what the variance of the projections. And what is the variance of this projection going to be? So we can show that it is U1 transpose S U1. Why? It's not so hard to show because this power 2 that you can see here, all you need to do is to write this power 2 as this entity inside the braces time itself. And pay attention, this entity inside the braces, it's a scalar. So you just need to multiply it by itself. And U1 transpose is common in both of these. So you can factor it out and write this as U1 transpose times xn minus x bar. Right, and then what you need is you can multiply it by itself, right? But since it's a scalar, I can easily write it as its transpose, because as long as it's a scalar, the transpose of a scalar and the scalar itself are the same thing. So if you don't mind, I can write this as the transpose of it. Then you will get here xn minus x bar, the whole thing transpose, times U1 transpose, which is U1. And then it is going to be 1 over n times U1 transpose, or U1 transpose can come out first, this term. Then you have these two multiplied together by 1 over n, of course. And remember, this was a summation, so you have to do the summation here. And it is going to be xn minus x bar times xn minus x bar transpose, and then this whole thing times U1. And then this term here inside this red braces is exactly this guy, which is the covariance of the original data. Therefore, I can write the covariance of the projected data as U1 transpose, covariance of the original data times U1. And this guy is the thing I want to maximize. I want to maximize this U1 transpose SU1. There is only one other thing I have to consider for my cost function, and the fact that U1 is a unit vector. So I need to, because clearly this is a what? This is a function of U1. I want to find the U1 that makes this variance maximum, right? The unknown here is U1. What's U1? But U1 has a constraint on it, and that's magnitude of it equals to 1. And so since it's an equality constraint, I add that constraint as something equals 0. Remember, U1 transpose U1 equal 1. This is the magnitude of U1 squared equal 1. That's your constraint. You bring the negative 1 to the other side, make it equal to 0 like this, multiply it by Lagrangian multiplier, and add your actual function to it. So here you combine the constraint and the function together and perform the constraint optimization. And guess what? If you take derivative of this cost function that you want to maximize, if you take derivative of this function with respect to U1 and set it equal to 0, here I showed you with simple linear algebra, this is going to be the result. So the result is this: SU1 equals lambda 1U1. And for all of you who know linear algebra, this equation is a very clear known equation. That's an eigenvalue problem. So what does it say? It says lambda 1 is an eigenvalue of the S matrix, and U1 is a what? An eigenvector of the S matrix. So clearly you can see that if I can solve for eigenvalues and eigenvectors of the S matrix, then I can find what? U1 and lambda 1. Now, we don't care about lambda 1 here. We care about U1. So just by getting the eigenvector of S matrix, it's over. Right? So that was U1. Now, when M was 1, when M is more than 1, you have bigger dimensions to reduce to. The problem is going to be the same exact formulation with the same result. So not only U1 is going to be what? An eigenvector of the S matrix. In general, all of these U's that I mentioned, they are all what? They are all eigenvectors of the S matrix. And S was what? The covariance of the original data. So that's all we need to calculate. This covariance, we calculate it, we find its eigenvectors, and then these eigenvectors, some of them will be what I want. Now you might say, why some of them? Well, guess what? What's the dimension of this S matrix? The dimension of this guy is definitely going to be what? It's going to be d by d. Right? Because remember, this xn and x bar, all of these guys are d by 1. So this whole thing is d by 1. When you transpose it, it's going to be 1 by d. So the result is going to be a d by d. Your covariance matrix is d by d. And d in this case was how much? 10,000. So we talk about it, of course, I know. Definitely raise the question mark in your minds. Isn't that a costly operation to calculate eigenvalues of a 10,000 by 10,000 matrix? For sure it is. We talk about what we do, but let's say you can find all of the 10,000 eigenvalues and eigenvectors. You don't want all of them, you only want one. You only want 6 of them. Which 6 out of all these 10,000? Which 6? Well, remember what the goal was. The goal was to maximize this function, right? The goal was maximizing. So if I want, look at this function. If I want this function to be maximized out of all different eigenvectors, which U do I choose? Of course, the U that gives me the biggest possible answer, and that comes from what? Yes, the eigenvector corresponding to the largest eigenvalue. So U1 is going to be what? U1 is going to be an eigenvector of S, but which one? The one with for the largest eigenvalue. Okay, if that was 1. If there are m of them, then what? Then in general, U1, U2 to UM are going to be the eigenvectors associated with what? With m largest eigenvalues. So when you do the eigenvalue calculations, you look at the m largest eigenvalues. You find which ones are the m largest, and then the eigenvectors of them are going to be what? U1, U2, all the way to UM. Okay? That is how you're going to find the U's. And once you have U's, then you can do your projection. The second formulation is called minimum error formulation. What is this one? It says, if you have d orthonormal d-dimensional vectors forming a basis and call these vectors U1 to UD. If you consider any data point in this subspace Xn, you should be able to write it as a linear combination of these U's, right? You can write Xn as alphas, summation of alphas times U's, where alphas are the dot product between Xn and the U's. So Xn can be written as summation of these alphas times what? Times U's. We know that one, right? As long as they form a basis, we can always do that. Now, what is the goal here? The goal is, instead of using all of these u's and the projection with all of these u's, we are going to use only a subset of these u's, subset of the basis, where instead of u1 to ud, I have u1 to um, and m is less than d. Using these, can I still write the data xn? Well, here, for that portion of the projection that I'm using what? I'm using the ui's and the projection on the ui's. I write it as summation I goes from 1 to m of zni ui, where z here plays the exact same role as alpha. And calculation of z also is the exact same thing as alpha, right? So if alpha ni was xn transpose ui, then z ni is also what? It is also the xn transpose dot ui. No difference. Okay, absolutely what? No difference here. These weights are the same. But I only have m of them, not all d of them. So what do I do for the rest of it that I do not do projection here? For the rest of it, where I goes from m plus 1 to d, I still use the rest of the ui's that I have not used in the first part, but these coefficients that I used this time for these ui's, these bi's, are going to be constant. So these bi's are not going to be xn's times the ui's. No, these bi's are going to be what? Constant. Clearly the zni's are not constant. They do depend on what data you're using. Bi's are going to use a very simple approximation for them. So as long as the u's you treat them as constant and the b's constant, it seems like this whole term can be like a constant. Now, of course, u's are unknown of the problem. You cannot treat them as constant, but literally in the second term, you are not doing any projection anymore. So this term, if I want to make it in plain English, this one has projections in those z terms. This one does not have projections. And because it does not, then definitely the result you get out of adding these two terms together is not going to be equal to xn. It's going to be an approximate of xn. We show with xn tilde. And so xn tilde and xn are not the same. The goal is to choose the ui's, which are unknowns, these gains bi's, right? Z's are not really independent. They are not really. They are functions of x's and u's. So once you have u's, z's will be determined. So I'm not going to call z's really unknowns. The unknowns are really b's and u's. I'll show you. You can easily find z's, as I said, or as I said, z's are these dot product terms. So how can I find u's and b's such that the difference between x's and the x tildes, the approximation of them, is minimum? So the cost function I defined this time is going to be called distortion function, which is simply the sum of the squared error terms, right? So xn minus xn tilde, square it, divided by the number of data. This is what we call a distortion. It's definitely a sum squared error term. And again, my goal is to find the small b's and the u's such that this term is minimum. So that if I brought the number of the actual u's that I'm using with their projections from d to what? To m, I'm reducing the dimensions, my error is minimal. So if you take derivative with respect to what? with respect to these three parameters, then one of your equations is going to be zn's are xn transpose u's, and that's exactly what I told you over here. So that's obvious. If you take derivative with respect to u's and b's, you'll get that b's are going to be what? The projection of the average x bar along each one of those u's. Clearly, as I told you, this one does not depend on xn. Now, it doesn't mean it's constant. Each one of the b's is constant. Not all of them are the same. Each one of these individual b's is constant. Why? Because the u for it is constant and they are all using x bar to project. Okay? So each individual bj is a constant term. It doesn't depend on xn. This is the formula you find for bj. And if you plug in this zn and this bj already that you have, if you plug them up to your x tilde formula, then you'll see that your x tilde is going to be xn minus this term here. Or if you take x tilde to the same size as xn, the difference between them, which is your error term, really, is going to be what? Summation I goes from m plus 1 to d. Those eigenvalues I did not use for projection in the second term. Summation over that of what? The difference between each term and the average, transpose of it times u. So this is a projection times u. So what is this? This term here is the deviation from the center for each point. You project it along u, that gives you a scalar, and then that scalar times u, summation of all of those, will be an error term. Remember, xn is in Rd and xn tilde is in Rd. So even the difference between them should be written in Rd, and that's exactly what you're doing. You're using the unit vectors of that Rd, and you're multiplying those unit vectors with a bunch of gains, with a bunch of constants, and these are those constant terms. Now, if you take the norm of this, square it, and divide it by 1 over n, that's your cost function. And that cost function would definitely be a function of what? U's, because you clearly see there are u's in it. So if you do that and simplify and plug in, your j, the cost function, the distortion function to minimize, is going to be I goes from m plus 1 to d of what? ui transpose s times u, where s is the same s that you had earlier. It's what? Is the covariance matrix of the original data, the d by d matrix. So you see, remember here I had this term, right? U transpose SU, you still see that over here. U transpose SU. And now the goal is to minimize this j with respect to ui. So now you set the derivative of j with respect to ui equal to 0. If you do that, this is going to be the equation that you will get. SU equals lambda u. And guess what? Yes, we know this. We already had this up here, right? This is an eigenvalue problem, which tells you the u's have to be eigenvectors of what? The S matrix, and lambda's eigenvalues of the S matrix. So how do we find the u's? By eigenvectors of what? The S matrix. Now here, the question is this. Which u's out of all these eigenvalues of the S matrix, which u's would you select here? Last time, if you remember, the goal was what? The goal was to maximize a function. Remember? The goal was to maximize this. So which u's did we choose when we wanted to maximize? We chose the U's associated with the largest eigenvalues, right? This time, what are we trying to do? We are trying to minimize a function. So which U's here should we neglect? Because remember here, these are the indices of the U's that you are not using in the projection. You are not using them in the first term. Remember? These are these guys, the second one. The ones that you don't use for projection. You only use the first M ones. The rest of them you don't use for projections. These are the U's that you are really neglecting. You're not directly using. Which U's should I neglect? You're right. The goal here is to minimize the function. So out of the U's, which U's should I neglect? You're right. Here, these U's are going to be eigenvectors of S associated with the d minus m smallest eigenvalues, because the goal is to minimize a function, so we should use the smallest eigenvalues, and the eigenvectors of them are the ones I should choose here for J. Those bring J to its minimum, and that's the goal that we want. So you see, either way of formulation that you go, the result is the same. Here I did some cleanup, and then so we found how to choose the U's. We found that it's an eigenvalue problem at the end of the day for the covariance matrix. That's what it is. And now the cost function, if you plug in all of these calculations in the cost function back here, you can see that your cost function, the distortion here, is going to be simplified to what? Summation of those eigenvalues that I did not choose, that I discarded, which are the d minus m smallest ones. So if I add all of those lambdas together, that is going to be your J, correct? Now, one thing here about the lambdas is when you look at the lambdas of a covariance matrix of some data, the lambdas are not typically all similar magnitudes. You have a few dominant ones out of lambdas that are very large. So let's say this is your first lambda, this is your second lambda, this is your third one, fourth one, fifth one, sixth one, and once you pass a few, most of the time less than 10 eigenvalues, the magnitude of the rest are literally close to zero compared to these first few dominant ones. And so those are those lambdas, and those are the U of these lambdas are the one you choose for projection. The rest of the lambdas, that's for them, all of this summation is going to be a very, very small term. So anywhere from here on, that's where it goes to this formula. Those will have minimal distortion. Those will have not a huge contribution because their lambdas are very small. And that typically happens in any machine learning with any system of data. It's mostly really related to data, not the algorithm. In any set of data that you look, you don't have like, if you plot your eigenvalues versus the index, the number of the eigenvalue, you will never see a plot like this. That it takes forever for this magnitude of lambda I to come and finally get close to zero. It's not going to be a very small slope. It's most of the time like an exponential function or something. Very, very fast, the magnitude of the rest will be almost zero compared to the first few. That's what allows us to perform principal component analysis, to neglect a lot of them, which have almost no contribution to compared to the first few ones, without having too much of distortion. Okay, that's the power, and that comes almost naturally in most of the data that you see. And so here, if you look at the distortion versus how many data points you have used for these these number threes, the pictures of number threes. So each one of these is, I assume it's a 28 by the original ones, not these ones. These are the bigger versions of the images, the 100 by 100. The original ones of these 3 by 3s, they were like 28 by 28 pixels, but these are enlarged and a lot of padded space are added to them to make them 100 by 100. But if it was like 28 by 28, then D here was originally 28 squared, which is 784. So here is the cost function plot for this data, this one. And if you plot it all the way down to 784, which means you are using all of the data, all of the lambdas, of course your what? Your distortion should go to 0. Here is perfectly 0 because you are using all of the eigenvalues and eigenvectors. But if instead of 784 I use maybe what? Only 200, I'm still what? I'm still almost at 0. If instead of 200, or let's say this is 300, if I use what? 100, still the distortion is a very small number. Okay, so in this case you clearly see that you need a bunch more of the numbers, but depending on how much distortion you can tolerate, then you might go even for what? You might go for 50, for 40 or something. So the number of U's, the number of eigenvectors, it's a good idea if you can do this plot, and it's by no means hard. All you need to do is what? To do this summation. If you do this summation, and you have to recalculate this, or you don't, because you already calculated lambdas one single time, so all you need is to recalculate this summation depending on how many numbers you are choosing, and then do this J plot, J versus M plot, right? Once you do this J versus M plot, then depending on how much distortion you can tolerate in your system, or there is another way that I'm going to tell you, depending on that one, you can choose a good number for M, because that's the next big thing. Here, fine, I found what the U's are. How many U's should I really choose? That's the big question. What is a good number for M? And so, as I told you, either you can tolerate so much of J, but many times understanding J and understanding the error in J is not the easiest thing in the world. So another way that you can do it is a ratio. So let me talk about the ratio right now. What is the ratio method? Here, this is what you do. You divide summation of the eigenvalues that only go from 1 to m, the one that you keep, divided by all of them. And then set that to a ratio. For example, you say, I want sum of the eigenvalues I keep divided by all of them to be 95%, which means what? Which means, if I want to put that in English, plain English, it means U1 to UM, the one that I will use, can describe 95% of the variation or the variance among the original data. Right? It means If I want my original data to be separate from each other, remember this cluster example, I want these clusters to be separate from each other. If out of all of those data, I only use m of them, then I choose m such that 95% of the gaps between these clusters is preserved. If I go from the higher space dimension to the lower dimension space, from higher dimension space to lower dimension space, I still can keep 90% of these gaps, 90% of the variance among the clusters, although I have removed a ton of the data, right? I still can keep 90% of 95%, 99%, you choose this threshold of the variance. I can still preserve that much of the variance among the data. And then how would you decide that? Based on the m. That m will tell you what? If you look at the plot, you have to do this plot. This plot is going to be like versus m, and that is going to be this ratio, the first summation over the second summation, right? If you do that, you see this plot is going to go up like this very fast. And the maximum it can reach is 1, of course. So as long as it reaches like 95%, the m value corresponding to that is the one that describes 95% of the variance. You say that is enough for me. Okay, and let me show you that right here. So here I wrote a sample demo code for you. So here you can see I bring in my data, right? Data X, which has 13 variables in it, and I have 199 xn values. So I have my data points are almost close to 200 data points, and each one has 13 dimensions. Okay, these 13, and n is how much? 199. The first thing I calculate is the covariance matrix, okay? So you can either use the built-in function cov that I'll show you, and I used, or you can use what? You can use the original definition that you can see we have. It's up to you. If you have the toolbox, you can use that. Otherwise, you can use the simple formula, the simple summation, and get the covariance matrix. In this case, it's going to be a 13 by 13 matrix. Now, you might just want to say, why did you use a transpose here on the data and then pass it to covariance? It's because of the way that the covariance is written. If you look here in the help, you see that it says covariance for a matrix A, or X in our case, has columns representing random variables and rows representing observations. So rows of the X matrix for me, if I want to use it with cov, the X should have rows to be x1, x2, all the way to xn. That's how this command wants it to be. And the columns are like variable 1, variable 2, correct? Variable 1, variable 2, all the way to variable 13. You have to have such a structure to pass it to the command cov, but if you look at my X is exactly opposite of that. Instead of being what? Instead of being 199 by 13, it's 13 by 199, correct? That's why I used what? I used the transpose. So don't be surprised that you see the transpose here. Then what? Then I found the eigenvalues and eigenvectors of the S matrix using the command eig. It's a built-in function in MATLAB. And when it gives you this eigs, what MATLAB does, it sorts it from smallest to largest. So your first eigenvalue is going to be the smallest. The last one is going to be the largest. And the way we put the formula down here, we assume that we use the first m eigenvectors and eigenvalues. And since we decided that this U ought to be the largest, then what? Then we definitely, it's a good idea if we can sort it such that the first one is the largest, the second one is the second largest, and the last one is the smallest, exactly opposite of MATLAB. That's why here I use what? The sort command. And here it should be diag, not eig. It should be diag. I don't know. It's probably my hand touched something or so. Because this D matrix that MATLAB gives you for eigenvalues, it is a diagonal matrix and it has a bunch of zeros and everything. So I'm only interested in the diagonal of it. So I get the diagonals. And then what? I sort it in a descending order. So the first one is the largest, the last one is the smallest. And because I did that, then the V, which has all the eigenvectors, since the elements of D are flipped, I have to change all of the elements in V as well, all of the eigenvectors in V. That's why I do a flip left, right of what? Of the V matrix, okay? Because that way I can keep the order. Again, remember here, this V is like this. It's like U1, U2, all the way to U D. And this D matrix is like what? It's like lambda 1, lambda 2, all the way to lambda D and a bunch of zeros. First of all, I use the command diag to only collect these. And since this one was what? The smallest in MATLAB, that's what it does. And this one was the largest, but I wanted the opposite. I wanted the first one to be the largest. I did a what? I did a sort on this. And because it brings the last eigenvector, make it the first one, so you have to do the same thing with eigenvalues. You have to do the same thing with eigenvectors. You have to make the last eigenvector be the first one and swap. That's why I use the what? A flip left, right. Basically make the left of the matrix the right of it left, and swaps. So that's what you can see here. Now that I have the lambdas and the u's, then what do? I do generate that plot I just told you, that ratio plot. Remember this ratio plot, which will tell you basically this one here, which will tell you how much percentage of the variance in the original data is explained by what m number, by how many of the eigenvalues. So here you see I'm dividing some of the lambdas from 1 to I, dividing by all of the lambdas for each I, and then plot it. And once I do the plot, let me stop here. If I run it, it can give you the plot I told you. If you look at this plot, you clearly can see that the value, the amount of variance in original data explained by the first eigenvector alone is about 64%. So the first eigenvector is very, very dominant. Alone, it's 64%. Now, if you bring in the second one, how much would it up to? To 99.8%. So just the two eigenvalues alone, 1 and 2, are going to explain to me 99.8% of the variation in the data. The rest of them are going to do about 0.2%, which is basically not doing anything. So I have 13 dimensions, but guess what? Only the first two are literally responsible for all of the variations. The other 11s are not doing anything, so I can discard them. So what number is good for me? M equal 2, because the first two clearly give me a ratio even bigger than 95%. or as I said, 99, still, even if you say 99%, still M of 2 is good for this case. And that's what the original also PCA command, because there is a command in MATLAB called PCA. I didn't use that one because it just gives you a bunch of numbers. You might not understand what's the meaning of any of these numbers. That's why I wrote a portion of the code really myself using eigenvalues and so on, so I can explain them to you. And if you go back, the parameter that is returned in the PCA default command of MATLAB is this guy called explained. You see, in general, it can return to you up to 6 outputs. The output I just talked about is this guy called explained. How much, you can see it here, returns explained, the percentage of the total variance explained by each one of the principal components and mu. So 99.8% of the variance can be explained only by the 2 first principal components. So M of 2 is definitely more than enough for this case. You don't need more than 2. M is 2. That's how you choose M, right? So that's what I wanted to explain to you, how you choose M, or using that parameter explained as you saw. By the way, as I told you, you can look at the eigenvalues alone. If you look at lambdas here, look at their values. If I show you their values, look. These are the first 2 numbers, 3.22 and 1.77, but the third one, look how small it is compared to these guys. It's about 8 over 1,000. It's almost 8 over 1,000. This is 2 over 1,000. Compared to what? Right? Compared to 1.77 and 3.2. So you see you have 2 huge dominant eigenvalues. The rest of them are literally not doing anything. Right? So you can generate also the lambda plot that I showed you, this one. Or you can calculate the J now. How much is J? J is sum of all of the eigenvalues you discarded, which is basically sum of all of this. If you add all of those together, which here I did in the code for you, how much is that going to be? Let's see. I guess I did not choose M. You have to choose M from that plot. Now if I do it, let's see, how much distortion am I going to get? Some squared error. It is going to be 1,000, which is nothing compared to if I wanted to use one of the first 2. Then this J would be in 10 to the 5 or 6, as this plot can tell you. You see? So definitely the plot of J versus M is going to be not only like this, a lot sharper than that. You can plot this J if you want a lot. You can generate the same plot J versus M. Here I just did J for the M I have chosen. But if I wanted, I could have this M be variable anywhere from 1 to 13. For each one I calculate the J and generate that plot. You know what? Let me add that code to the sample code that I'm going to upload and put it under video description. Let me add it right now just for the sake of your demonstration. Okay, so I just added those. This is a plot for the lambdas that you can see. This is the ratio plot that you can see, and this is the plot of J versus M. So if I run it now, you should be able to see all of the plot. This is the plot of J versus M. For this case, you clearly can see that it is not going to go gradually, although this is even very fast, but it's not going to take like 200 or 300 or something like that for the sake of this data I have. For a set of image data, it might take a lot more, but for this case, you clearly see in about 2, M of 2, it literally goes down to 0. Okay, so the choice of M equal 2, you can clearly see it from this plot. So I showed you the plots for that data X that I have, but if I want to show you something about the images of those number 3s, the handwritten ones, what you can see here in this plot is basically, so these threes that I meant, different ways to write it with hands. These are the four eigenvalues, the four largest eigenvalues for those handwritten images, and these are the eigenvectors. So each one of them, this is like u1, u2, u3, and u4. This is the average of those images. Why do I need average? I'll tell you in a second, but you see these are different eigenvectors. So the good thing for these images, you can visualize them very nicely and see what they mean, because for the sake of this data I used in my code, my data are like they were 13 dimensional. You could not really imagine them. So when I brought them down to 2 from 13, you really feel the effect of it. But the good thing with these is you can convert them into images and then visualize the images. Now, what's the meaning of these? It's not that clear. I mean, if I want to explain U1, U2, U3, and U4 is not as clear as when I do some simple data. For example, we're going to talk about it in a minute, but here you see I have some data, some random data that are spread over the XY plane, and then if I find the principal components for them, they're going to be U1 and U2. Okay, if I use both U1 and U2, I have not done any compression of data because the dimension was 2 and now I'm still using 2. If instead of U1 and U2 I only use U1 and project all of XY points onto the direction of U1, then I went from D of 2 to M of 1. I have done like 50% data compression, right? And clearly here you can visualize the meaning of U1 and U2. U1 is the direction along which the maximum spread of the data is happening, and U2 is the orthogonal direction to that. Okay, so these are the principal directions of variations, just like what you had in solid mechanics or statics for a shape, right? You had principal moments and principal directions. This U1 and U2 are the same thing for the spread of the data. So here you can visually see the meaning of U1 and U2, right? But when it comes down to images, if I tell you what's the meaning of U1, U2, U3, and U4, they are not as clear. You might say, well, they could be those degrees of freedom you initially talked about. You said if I want to write 3, then different ways that I can change the appearance of it is by horizontal and vertical displacements, rotation, scaling, line thickness, and so on. And to some extent, yes, you can see a little bit of that in these images, but not perfectly. For example, if you look at U2, you kind of see, if you look at the yellow versus purple, that they both appear on U2. It's kind of like a vertical shift to me. Or if you look at U1, to me, it looks like a rotation. You clearly see this direction became this direction, right? If you look at this one, it's not as clear. U3 is not that clear, whether it's any shift or anything. U4 to me looks like a line thickness or a scaling in the X direction, because you went from this to something much wider, right? So it's like a scaling in the X direction. And by the way, you need a bunch of these U's and lambdas. If you remember for the image, when we look at the graph, I told you that the lambdas don't drop so fast. So 2 or 3 of them is not enough. You need a bunch of them if you want the small distortion. You need a bunch of them, maybe 100 or 200, maybe something like that you need in order to preserve the image, right? So to a good extent, if you want a very rough thing, then maybe a first 5, first 10 is enough. But if you look into the rest of these U's, then probably somewhere in them you might see something like a horizontal shift, or like a scaling in the vertical direction, or a line thickness, or something like that. But again, deciphering these U's for images is not as simple as when you are working with 2 or 3 dimensional, those circles or dots or something. Here they are a little bit harder to interpret. Okay, so this is one thing. Now, of course, the more m's you use, the more terms you use, the more eigenvectors you use and keep. Basically, the smaller the compression that you do, the better the image that you will get, right? So for example, here, if this is your original image, here, if I only use one of the eigenvectors, this is the approximation to that. If I use 10 of them, you see it's getting closer. If I use 50, I'm getting still better. If I use 250, then it is almost identical. It's not perfect. It's going to be perfect when m is equal to d. And as I told you, for those images, the original images were 28 by 28 pixels. So the perfection is going to happen when the m is going to be 28 squared, which is 28, not 27. 28 squared, which is like 784, right? But after about 250 and so on, you don't see any visible difference. And that's kind of like here, that's 250. After 250, as you can see, the amount of distortion is close to 0. So if you reconstruct with 250 eigenvectors instead of 780, which is a huge amount of reduction in the data, the difference is not something you can easily recognize, right? So still it's a lot of compression. Instead of 784 eigenvectors or directions or dimensions, you only need 250 of them for a very, very good recognition. Maybe your algorithm for classification, it's just enough for it to just use 50 of the data, or maybe 10 of the data, or maybe 1 of the. So depending on how your classifier performs, any number of these m's might be able to work with it, and you get a lot of reduction in the data. Now the question is, how do you do the reconstruction or the approximation? Because each one of these is an approximation to the original one. How do you do approximation? This approximation is your what? These guys. This is your original xn, correct? And each one of these is your what? Your x tilde of n. So how do you get the x tilde? If we go back to our formulas that we have and replace the z's and the small b's that we found, remember, in the formula, then x tilde can be simplified to this guy here. So this is your approximated data, x tilde of n instead of original xn. How do I form it, or what do I need to form it? What do I need to get my approximation? The data that you need to do the approximation is x bar, as well as what? MUIs. So if you want to do the approximation, you need MUIs and x bar, and that's why in this image you see that not only I showed you the UIs that you need to keep, I also showed you what? The average, the x bar. That also you need if you want to what? If you want to make these guys. If you want to make them, you need all the UIs that you want to keep, the 10, the 50, the 250, plus the average, which is this guy. Right? And now you might say, where is the reduction coming from? You all the time talk about dimensionality reduction, compression, data compression. Where does it come from? Well, I'll tell you where it's coming from. So if you look here, what was the dimension of the data xn that you need to keep? For xn, you had n data points, and each data point had d dimensions. So you needed to store these many values, n times d, correct? You had dxn's, which was n times d values to store. Now, when you want to store what? The xn tildes, how many values do you need to store? So you need to store x bar. You need to store what? MUIs, as I told you. And then what? What are these guys here, this term? This is a scalar, right? This is a scalar. This is a weight. This is a weight, a scalar. Weights of what? Weights of the UIs. How many of these weights do you have for each xn? M. Correct? You need what? You need MUIs, and you need what? M weights, because I goes from 1 to M. So M of these will be multiplied by M of these U's. So you have M weights or scalars. So plus what? M weights per xn. So per xn, you have m weights, m scalars, you have MUIs, and you have x bar. And what's the dimension here? Your x bar has the dimension of x, so it is n by 1. Your UIs also have the dimension of x bar, so they are also n by 1. And these are scalars. So here you have what? You have 1 n by 1, you have n times m by 1, and you have m times 1 m scalars, but per xn. And how many xn's do you have? N. So what is going to be the total number of data? It is going to be 2nm plus n, or it's going to be n times 2m plus 1. So this is the number of data values that you have to store compared to what? N times d. So for our case, this n, for the code that I showed you, n is what? 199, and d was 13. Now, if I use only the 2 data point, the 2 m of 2, this is going to be 5, this is going to be 99. So what's my compression rate? This number divided by this number, so my compression rate is 5/13 of the original data I need, which is clearly less than what? Less than 50%. You see? So if I want to do that here, 5/13, 38.5%. So I only need 38.5% of my original memory to store this data compared to what I had, right? This is a big compression, almost a compression of 3 to 1. Yes? So you clearly see that's one of the applications of PCA is data compression and, of course, dimensionality reduction. So you clearly see that over here. So when I come down here and say the first application of PCA is dimensionality reduction, of course, that's the base of PCA, but where would you use it? In data compression. What kind of data compression? A lossy one. It's definitely a lossy. Lossy means what? Lossy means you cannot get the original data back if all you store is this guy here. If all I store is this data and I threw away the other 11 UIs, remember, out of the 13 UIs, I discarded 11 of them. I only kept 2. Correct? If I only keep this 38% of the data or 38% of the numbers, and threw away the rest, I could never get the original picture back, by no means. It's going to be lossy. If you look at each one of these, you clearly see the distortion compared to the original one. Now, of course, for our eyes, here for m of 250, I'm doing what? I'm doing compression, right? Because remember here, D was 784. So I'm still doing a huge amount of compression, but you might say, well, it doesn't look like it is lossy. It is, but those details that you don't see here, which here they exist, they are not something our eyes and your eyes can what? Our eyes together can see. They are beyond our perception levels, so we can easily neglect it. So here, if I do a compression with m of 250, and if it's a picture or video or something, still the quality of it is good. But if I do m of 3 or m of 10, you clearly see a lot of distortions. That's the same thing you see with videos, right? If the amount of compression in a video is huge, you see a lot of pixelations and distortions. While if the amount of compression is a little bit moderate, not extreme, the video quality is still reasonable, but of course the amount of compression you get is not as high as when you did m of 10 or m of 50. So it's a trade-off. Image quality versus data compression, but whatever you do, it's a lossy. Whether that loss is something we can perceive or not, that's a separate story. Okay? So that is the first application of PCA, and by the way, as I told you, how we can reconstruct, which by the way here, let me show you in my MATLAB code. So in my MATLAB code, you see here that, let me show you. So in my code, here you see I calculated x bar, and then I used the same formula I showed you to calculate what? X tilde. And here in this case, in my code, x tilde and x are the same dimensions. But remember, if I want to store x tilde, I'm not going to store them the same way they are. If I want to store the x tilde, I'm not going to store x tilde directly. I'm going to store, as I told you, x bars. The two u's that I need in this case, because m was 2, so I'm only going to store u1, u2, x bar, and I need these coefficients, this guy. This guy I need, as well as what? This one. Correct? I just need to store these two numbers because these are numbers, right? Look, when I equals 1, the first data point, look at this guy. This is just a coefficient, -48, and this other one is also what? It's also another coefficient, 96. So all I need to store is that -48, 96, u1 and u2, correct, is 13 by 1 vectors. This is u1, u2, and x bar. And that's enough for me to restore construct x tilde number 1. So I can add something, say storage. If I want to do storage, I need to what? I need to do x bar, u1, u2, and then all of these what? All of these coefficients. So what I can do is I can use some coefficient matrix. And for this coefficient, once I go for I of 1, then I say what? Coefficient of I and 1 is going to be this guy. And then coefficient number 2 is going to be what? Is going to be this one. So here we go. Then I also need to store what? The coefficient. And that's it. So let me go ahead and run it. There we go. So now you clearly see my coefficient is 199 by 2, not what? 13 by 199. I really need the coefficient or yeah, that's good, coefficient or coefficient transpose. Correct? So I'm storing a 199 by 2. I'm storing 3 vectors, each one of them is 13 by 1, instead of what? Storing, as I told you, data that is 13 by 199. So the amount of compression for me is 2 times 199 plus 3 times 13 divided by 13 times 199, and this number for me is about 17%. I only need to store less than 17% of the data in this case. So that is clearly what a data compression. And that's not the only application of principal component analysis. Sometimes you do PCA, but you don't choose M less than D, you actually choose M equal to D. Your goal is not to do any dimensionality reduction or compression. So you might say, what's the goal? The goal is to decorrelate the data. What do you mean? Well, if I go back to this picture I just showed you a few minutes ago, if you look at this picture, here my original data, which are spread inside this kind of tilted ellipse, there is a big correlation between the two pieces of the data. Here I have y and x for each data point, and clearly my y and x are correlated. I can see that if my x is increasing, right, on this line, my y is increasing. If I go down, x decreasing, y decreasing. So there is a big time correlation between x and y. What do? I say here the dimension is 2. I have only x and y. My goal is not to go down from dimension of 2 to 1. I just want to stay in 2 dimensions, but the data I want to choose or use is I want to make sure there is not a correlation between them. So here I form the S matrix again. I find the 2 eigenvalues, and they will be U1 and U2, which you can see in this picture. And what is U1 and U2 showing? As I told you a few minutes ago, U1 is clearly showing the direction of maximum variation or variance among the data, and U2 perpendicular to that, because these guys are forming a basis. So now if I rotate my data with a simple projection, I dot product each x and y point by U1 and by U2, then this data is going to be rotated. So it is going to be like this now. If I look at it in some new coordinate, in this new coordinate, my data is going to be like this, where there is no necessarily clear visible correlation between x and y. I mean, if you look at this data, I can go up in this direction, and if you look at the data, when the x is increasing, the y might increase too much or not, because if you go along this direction, the x is increasing, the y stays the same. If you go in this direction, the x is staying the same, the y is increasing. If you go in this direction, both of them are increasing. There is no dominant direction or correlation between the data. Good? So decorrelation of the data is very important, because if you want to use some data points, in this case x and y, for any classification, they better not be correlated. Otherwise, they are not going to give you any good classification power. So decorrelation of the data is important. And not only you can do decorrelation with the principal component analysis, the other thing you can do is what we call sphering the data or whitening the data. What does that mean? It also forces the data the way I'm going to show you. You can force the data to have a what? To have an average of 0, and then what? A covariance matrix of identity matrix. So you can force the transform data to have a mean of 0 and a covariance of identity. What does that mean? It means if your data has a bias of non-zero, the average of the data is not 0. You clearly see here the average of my data on X is like 1 and on Y is 3. So the center of the data is not at 0 and 0, which is here. I can shift this data in this new coordinate. As you see, the center of my data is at 0, 0, and I can force it to have a what? To have an identity covariance matrix. When this S becomes identity like this, what does that mean? Well, this is the variance of X, this is the variance of Y, and by X and Y I mean new X and Y. So if you call it Y prime and X prime, this is the variance of X prime, this is the variance of Y prime, and these two are the covariance between X prime and Y prime. When it's 0, clearly means those data are not correlated, as I told you. And when the variances are both equal to 1, what does it mean? It means instead of the data spread being like an ellipse, now the data spread has to be like a what? Like a sphere. Because the variance of X and Y are similar. So what would you do? You convert an ellipse tilted, not centered at origin, you force it to be centered at origin, you convert it to a spherical spread, and the axes are not having to have any, the new data have any correlation. So because you make it look like a circle or a sphere, you might call it what? As I said, sphering of the data. And whitening here, whitening is referring to the process of no correlation. You are making the new axes to be not correlated, so they act like a white noise without any correlation of data together. Good, so that's why we call it decorrelation or sphering or the whitening of the data. Now, how do I do that? Here, again, I go and I find the eigenvalues and the eigenvectors of the S matrix, the same S matrix. Okay, the equation you have this time is the same as last time. S times U equals U times L. S is the same covariance matrix of the original data. L is a diagonal matrix containing the eigenvalues of the matrix S, and U is an orthonormal matrix containing the eigenvectors of the matrix S, right? So instead of writing it as SUI equals lambda I UI, if you write it for all of the i's and then combine, if you combine all of these equations into one giant matrix format, this is the result, this guy. Okay? Now, so finding the U components and the lambdas and then forming the L matrix, and the U matrix is by no means a hard thing, right? They are coming from eigenvectors and eigenvalues of the S matrix. Good? Now, what kind of transformation do you use to do this rotation? And it's not just a rotation, it's also some scaling in both directions and some translation, right? So this is a translation plus rotation plus scaling of the data. I did not reduce the dimension of the data. I did all of this to get it to what I want. How can I do all of that? It's very simple to show that your new data, yn, the transform data, is going to be what? The original data xn minus their average pre-multiplied by transpose of the U matrix involving all of the eigenvectors, and then pre-multiplied by the diagonal L matrix containing eigenvalues to the power 1 negative 1/2. If you do that, then easily you can show that the average of y bar, so summation of y ends, this one can easily show that this guy is going to be going to 0, because these two are going to be the same for all of them. When you do a summation over xn minus x bar, it's going to be summation xn minus nx bar, which is ultimately going to be what? 0. And if you calculate the variance of this new data yn, the variance of the new data yn, you can easily show it is going to be what? An identity matrix, which is what I just told you, an identity matrix. Correct? So all we need to do is to apply this simple transformation here, and that does the whitening of the data without, again, what? Sizing the data or compressing the data. It's just decorrelating the data, scaling it, translating it, and rotating it. Okay? So that's another application of PCA, very important. The last point I need to mention is PCA for higher dimension data. When we are, especially this is important when we are dealing with images. When you're dealing with images and you want to do some PCA for images, remember, just like these number 3s that we talked about. If you want to do that, then what? For these images, D, the dimension, is huge. Why? Let's say you are storing images, you are working with images that are like 600 by 800 pixels. Or if they are HD, right, each dimension is more than 1000 pixels. So D, in this case, 600 by 800 is going to be 480,000, or for the HD, it's definitely above 1 million, right? So D, the dimension is huge. If you want to consider RGB images, then that should be multiplied by 3, because you have R, G, and B channels. But if these are just grayscale image, so here I add for a grayscale image of those many pixels, D is that huge number. And when D is that big of a number, your S matrix, your covariance, is going to be that number by itself. So S is going to be 480 by 480,000 pixels. Now, if you want to calculate eigenvalues of this, guess what? It's not going to be fun. It's not going to be easy. It's going to be very, very expensive to calculate the first, let's say, 100 eigenvalues of this huge number. Okay? Now, in many cases, not in many cases, but in some cases specifically, the number of data points that you have is not as big as D. So the images themselves have huge dimensions, but you don't have as many images for the samples, for the training, for PCA, for anything. Maybe look at this case. In this case, D is 784, but how many data do you have? Only 5. You only have 5 pictures, 5 samples. So this N is much, much less than D, correct? In those cases, there is something that you can do so you don't ever have to go through calculating the eigenvectors and values of such a huge matrix. First thing is this: if N is very smaller than D, which happens in many cases, then you can easily show that from linear algebra, and I'm not going to prove it. You can take a look into that. That from the eigenvalues of the S matrix, d minus n plus 1 of the eigenvalues will be literally 0, practically exactly 0. Not approximately, exactly 0. So in this case, I have 784 and I only have what? 5 samples. So out of all of those lambdas, if I go and calculate all of the lambdas, what's going to happen if I'm only dealing with 5 samples? Then 784 minus 5 plus 1, right? N minus t plus 1, which is going to be what? It's going to be 780. Of them, of the lambda i's, are going to be 0. Only 4 of them are going to be non-zero. So if I only deal with these 5 images, only 4 lambdas are not going to be 0. And in this case, those are these guys that I showed you. Now, if I did PCA on these number 3s and I used a lot more images, then a lot of lambdas are not going to be 0. In this case, if you look, definitely for this training case, a lot of lambdas were not 0. If you look here, a big number of lambdas were not 0. So definitely when this PCA was done, 5 images were not used. You had a lot more images. Okay, but if you look at the rest of them, they are literally what? 0. Okay? So what can I do to avoid this huge computation? So what can you do to avoid that big time computation? So here you form a matrix X. Each row of that matrix will be an xn minus x bar. Okay? So what do you have? It's going to be like x1 minus x bar. Of course, the transpose of the whole thing. Then you have x2 minus x bar, the transpose of that, all the way down to xn minus x bar, the transpose of that. This thing, you call it that big matrix X. Now, what's the dimension of this? Remember, x1, xn, x2, every one of these is a d by 1, correct? They have d elements. So when you transpose it, it's going to be like 1 by d. And there are n of them. So the dimension of that is going to be what? N by d. You have n rows. Each row is 1 by d. So it's going to be n by d. That's your x. Now you define covariance matrix X to be covariance of this X, this matrix X. You see, it's 1 over n X transpose times X. If you want to find the eigenvalue or eigenvector of that S, then it's going to be the matrix times the eigenvector is equal to eigenvalue times eigenvector. Right? This is the eigenvalue, eigenvector finding of that covariance matrix S. Now, what you do is this. You first pre-multiply both sides of this equation by x. If you do that, what will you get? You will get 1 over n x transpose x ui is equal to lambda I x ui. And now you define this xui, you call it vi. So this guy here is going to be vi as well as this one. And this is going to be the result. What is this? Clearly, this is an eigenvalue problem. For which matrix? for this matrix, for the S matrix that we defined, but not the X matrix. It's kind of like the transpose of the S matrix. Look at this one. This one compared to S, the big thing is the dimension. This is X transpose X, this is X transpose. So here I'm solving for what? For an eigenvalue eigenvector problem, but for the matrix X transpose instead of X transpose X. The eigenvalues of this problem are the same as eigenvalues of the original problem. So the same lambdas they would share, right? They share the same lambdas. That's the good thing. Whatever I find for this problem, whatever lambda, is the same as this problem here. And what's so good about the second one that is not good about the first one? It's the dimension, as I told you. What is the dimension of X transpose X, and what is the dimension of X transpose? Let's look at the difference. Remember that X is n by d. What is it? This is going to be d by n times n by d, which is going to be what? It's going to be a d by d. And remember, d is huge. D is in millions, in hundreds of thousands for an image. What about this one? Here you have n by d times d by n. So the result is what? N by n. And n is the number of pictures you have. So this guy might be like a 5 by 5. Right? Now you see the huge difference. Calculating eigenvalues, a million by million matrix or a 5 by 5 matrix. Right? They share the same eigenvalues. At least the first 5 lambdas that they have are the same. And guess what? I only care about the first 5 lambdas or first 10 lambdas or 20 lambdas or something. As many as I have samples. So I can get the same lambdas from both. And then what? How do I get U's? Because remember, I wanted the U's. This is what I wanted, U's and lambdas. I found the lambdas, the one I want. And U's can clearly come from the definition of this transformation. All you need to do is to find U's from here, or you can reformat it and write it this way, as you can see in the box. So if I want to summarize, what do we do for high dimensional data where you don't have a ton of samples? What you need to do, instead of defining the S matrix as traditional, and it comes down to a D by D covariance matrix for which calculating eigenvalues is very hard and time consuming, instead I form which matrix? I form X transpose matrix, which is what? This matrix. And this matrix is going to be n by n, much smaller dimension. I calculate the eigenvalues for that, the lambda i's, and I calculate the eigenvectors for that, vi's. And then if I want ui's, the original ui's in the original space, because remember, at the end of the day, I need lambda i's and ui's, or really ui's. Ui's is what I care about. I don't even care about lambdas. Lambdas I only care about when I want to decide what m to use. But really, if I want ui's, once I have the v's and the lambdas, then I can use this formula here that you can see and get what? Get the ui's. Good? So once I have ui's, I can do my PCA. Once I have the lambdas, I can decide on the m. So hopefully this long video on PCA was useful to you. And in the video description, I'm going to share with you my PCA demo as well as this data.mat from which I read my data. Thank you so much. I will see you in the next video.